Good day everyone, welcome to the second part of our section on loads, load combination, basis for design, taking real world phenomena and converting them into something we can use to analyze a beam or a column or a building and get forces that we can then design our building with, which we'll cover in the rest of the course. So in the first part of the video, we covered imposed loads and permanent loads in terms of combining them to get to load combinations at ultimate state, the STR and STRP, and then also at for deflections, the SLS, service stability limit state. We're going to now look at some other limit states and load combinations and various other factors in this second part of the video. So, as I mentioned, we've covered various other limit states. Now here, here are some other limit states that you may need to consider. For instance, you've got your ACC, or accidental limit state, which this is the September 11th crash with a plane going into the building. And here on the right hand side actually shows a damaged hotel building and a fire that broke out, and you'll see these beautiful map crack patterns that occurred exactly where the rebar runs. This was subject to a very severe fire. Other limit states you may have to consider is corrosion and durability, and so you'll see at the bottom there, this is actually part of what you need to do. In this course, we will pretty much focus most of the time on structural resistance, but in fact, serviceability and durability are always required as well. You're always required to satisfy those two as well. Now on the screen, these pictures actually a site that did a number of projects on, and they manufactured various chemicals, and the specific structure you're looking at is where they manufactured hydrochloric acid. Well, they used hydrochloric acid in the principle, in the process, and once in a while the hydrochloric acid would bubble out and come down. This is actually hydrochloric lying in the base there, and it would come down and it would eat away the column there, and you can see it's totally eaten away, this column. I mean, you could go up and pretty much put your finger or fist through the steel, it'd been eaten so away. And so those sorts of projects, you inherently end up over-engineering things. If you know your steel is going to be eaten away, you add on quite a few extra millimeters to make it last, and so it will no longer be serviceability or ultimate limit state that governs the design. It would be a durability requirement. Possibly you'll have to put a coating or sacrificial layer on it as well. And you'll actually see in the background, just as a matter of inches, you can see the new structure going up there, and this had to be the new structure had to be erected around the existing, and then what was even more fun, there was a main hydrogen feed line nearby, so there was no welding or anything else allowed because it could kind of blow up the area. So you had to be very careful looking at how to make this work in practicalities. So now, with all of those, I'm going to continue on from what we were looking at, now how to combine loads. And I've already been alluding to this quite a bit, but hopefully with going through this again, it will make more sense. We've got our STR, remember, permanent loading, 1.3 imposed, and 1.35 permanent, 1 imposed. And remember, this you could have 3 different times. You could have your wind load there, you could have a permanent load there, imposed, sorry, I keep swapping them around. You could have a crane load there. You could have any sort of type of single event imposed load going in at this Q position. Then we've got our STR case, imposed load leading. So we've got an imposed load 1.2 plus 1.2, and then remember what I showed you earlier, 0 times wind, 0 times wind. And so wind favorable means it makes the load less, so we try to have it as low as possible. Wind unfavorable, it makes the force worse, so use a different gamma factor, but in fact the combination, the psi factor, is the same each time it's 0, so it just disappears off. If we now have wind load leading, there's a wind load, there's a wind load, and you could see you could have permanent and imposed favorable or permanent imposed unfavorable. And so I mean up here I would also have a 0.9 G plus 1.6 Q case. So there you've got 0.30 because it's favorable, or 1.6. What happens with this is this becomes a waste of time. So it's not normally listed in your list of combinations. imposed load is favorable, imposed load's unfavorable, you know, all these different combinations, because most of them just disappear out the way, and you can do it by inspection. But in reality, if you put all the different wind load, well, all the different load combinations together, remember, a combination is what happens in real life. It's everything acting all at once. A load case is wind or dead or imposed, etc. And so these would just give you some different cases: permanent, imposed, etc., moving along. And then equilibrium, overturning as per STR factors for this situation. So now at the SLS, the failure criteria is given by the design resistance is less than the limiting design value of serviceability criterion for deflection. And we've already sort of covered that briefly from that. We're not, this, just as a note, we're no longer using the SANS 10160 part table D. Normally, you can primarily refer to 10162 part 1 for the calculations in the course, just so we are consistent. So just use the steel code. You don't have to worry about 10610 part 1 anymore. For steel, we can consider irreversible serviceability deflections, elastic. The SANS 10160 does actually supersede it. It's a newer code. Although we're just going to use this for now for simplicity, to keep everything in place. Just as a note, steelwork design is often governed by serviceability rather than strength, especially for floor beams and portal frames. Hence, it's often better to check such elements for serviceability first and then for strength. What do I mean by that? You're designing a beam. You don't want to run through all the calcs, check if it's strong enough, and then you go back and check if it's the stiffness is high enough, because to get a beam size for deflections is quite a quick task. So normally what you do is you first find a beam that satisfies deflections, or a structure that satisfies the deflection, and then you go check it for strength. And so, as I was mentioning earlier, so this is SLS, serviceability, 1.11, 1.6. So these are some sort of typical SLS load combinations that you get, so make sure you understand it. And the psi factor varies each time depending on what you're doing it. So now, what size beam would you be used to limit deflections on a simply supported beam carrying an imposed load? Remember, I was looking at 10162 part 2, where it just says look at the variable, i.e. the variable. Load of 10 kilonewtons per meter. I'm ignoring permanent load. The beam spans 6 meters, maximum deflection, variable load. So let's say it's a simple span of floors and roofs susceptible to construction finishes, not susceptible to cracking, 1/300. So 6 meter span, I can have an up to a 20 mil deflection. This is the equation for the deflection of a simply supported beam. Just be careful, W is the total load on the beam, which is equals to omega kilonewtons per meter times a length, times some length here. So just be careful. So it's omega, the distributed load, times L to the power 4 over EI, stiffness, second moment of area. And what we do, if we play with this equation, we can actually get the second moment of area we need out of that. So what we do is we can work out, I need an I of 42.2 times 10 to the 6. I now have a table of beam sizes. I can go to the beam size and just look down and run my finger down the column until I find a beam with a bigger IX, a bending moment, a bending stiffness about the major axis of value greater than this. And let's say in the red book, South African Steel Design book, I find the UB, Universal Beam 254. It's 254 deep, 146 millimeters wide, and 31 kilograms per meter. So that's height, breadth, and weight. And this has a suitable stiffness. And so you've just sized your beam. You have a beam size that should do it. And if you check strength, you probably will find it works out as well. So continuing on, imposed loads. I'm going to run through now what are imposed load in terms of magnitudes, etc., and permanent loads. You will have covered this previously in your courses, but just to remind you, imposed load can include a variety of items: people, furniture, maintenance, construction, wind, movable, water and fluid, stored materials. And so all sorts of these can occur, and these can lead to very high loads, especially on industrial floors. Imposed loading in the code consists of a UDL, a uniformly distributed load, and point load, which are not used at the same time. For small areas, the point load will govern, while big areas, the UDL governs. Imagine if you are designing a floor in an office building. Now, it's possible for that floor that somewhere they will have a very heavy safe or a very heavy filing cabinet. And so you might need to design for that filing cabinet, which weighs 500 kilograms or something like that. And it acts over a very small area. It's 500 kilograms and it's got a couple of small feet at the edge of the safe or filing cabinet. And so you would need to make sure that your building is strong enough, especially for punching, that it doesn't punch a hole through the floor. But at the same time, you're not going to put that safe on every square meter all at once for the entire building. So you have a point load for small effects, and then a general load which is sufficient for your beams and columns, etc. Now, just as a matter of interest, at times it may be necessary to go beyond what the code asks based on engineering judgment and site-specific requirements. There will be times when your client doesn't fall into the exact requirements. It's an office, but for some reason the offices of your client have very, very heavy loads. They have unusual equipment or lots of paper they store or something. You may need to be careful. The code does not account for vehicles which may enter your buildings and various other things. So that was now looking at some imposed loads. But now, when you have a large area being supported, just imagine now, I was talking about a heavy safe on a beam or a floor, and if I was designing what's immediately below this heavy safe, I would make sure that the floor is sufficient. But that might be a 20 or 30 kPa load. But now it's not going to be on every square meter. So now I get down to, let's say, a 5 kPa, 5 kilonewtons per square meter load on the beam or the floor. But now let's say it's a 20-story building. What is the chance of every floor in the whole building being loaded all at once? And that is fairly low. So as engineers, we want to produce economic solutions. It's easy just to over-design everything and be safe, but then you're just going to waste the client's money. So we have reduction factors that we apply. So for categories A and B, so you'd go have a look at what is category A and B, and so, oops, I can't remember what that is, so you would go and look that up. And you would see then what are your categories A and B, and this comes from domestic and residential areas, public areas not susceptible to crowding, and then we're going to use some of these other ones below when we go back through it. So depending on your classification of your building, you have a reduction factor, where A is the loaded floor area exceeding 20 square meters. And so what you do is you plug that area in here. The area is the loaded floor exceeding 20 square meters. You plug that in, and what you will find is you get to a factor above 0.5. It's always greater than half, but it's less than the total load. So let's say you are designing a column and the column carries 100 square meters. You don't need to assume every square meter is loaded all at once. You can reduce it. The same thing for categories D and C and D. You have an area, a reduction factor that you multiply by your imposed load just to get to a more economic solution. And so that you would apply to these loads here. So here you would have, for instance, an area for domestic and residential activities, and we are designing a balcony. And so on my balcony, I would use a 4 kPa, 400 kilograms a square meter. It's 4 big rugby players per square meter all at once, so they are really, quite tightly packed onto that balcony. And then a point load, a small point load acting over 0.1 by 0.1 square meter. So this is one rugby guy carrying his 2 friends to show off how strong he is, and he's standing on 1 foot. And so it's over a 100 mil by 100 mil area, and that's a sort of a punching load to make sure he doesn't punch a hole in your balcony deck. Similar things, we've got loads of 3 and 5, etc., etc. So remember, these don't act at the same time. The distributed load and the point load don't act at the same time. And so same thing, here is the values for category C, public areas where people may congregate, shopping areas, etc. There you've got much higher loads, 500 kilograms a square meter is quite a lot of load. That you really have to pack things up to get there. And that's on every square meter all at once on all the exposed surface area. Industrial, impose loads on to industrial use and storage. You say, here you go. And these rules often get broken. I mean, we had a client who we designed their inaccessible roofs for 5 kPa for that supposedly maximum load, because they have a big concrete flat roof on a in the warehouse they might have this little room with a flat concrete roof on top, and then they get some new equipment. They, hey, that's a great place, it's concrete, we will now go put our new switchgear or our transformer or some big piece of electrical equipment on top of that roof, which was never designed for any of that load. And we know of a case where they dropped a big piece of electrical equipment through a roof that someone else had designed, thankfully. And yeah, from then on else, we just over-designed all their roofs, because we knew at some stage in the years to come they would put something up there. They would store big, heavy material. And so that was an agreement between us and the management, and they were happy with it. At least then, if their staff did something silly, it was safe. Whereas on other floors, we might get to a 20 kPa floor load. I mean, we had floors where they would store big piles of material, and there you could have 2 tons a square meter of material being stored that you would need to design for. And so now continuing on, inaccessible roofs. What's an inaccessible roof? Well, that's where it's difficult to get up there, so chances are people won't use it to have a balcony party up there. It's not readily accessible, so you'd have large numbers of people up there. It's really basic access, up a cat ladder, and then you wouldn't be able to store equipment up there easily. Where an accessible roof is, it's not too difficult to get up there, so maybe people would store material there, maybe you would have a social gathering up there. You'd have to be a bit more careful. And depending on the size of what you were designing, your area, for areas less than 3 square meters, you design for 0.75 kilonewtons a square meter, and for area of 15 square meters and above, 0.25. So just have a look at how big is our design. And then for normal maintenance and repair, you've also got some loads you would use, and then you can interpolate between them. So if you are designing a 10 square meter inaccessible, well, a piece of steel that supports roof sheeting, that purlin carries 10 square meters. So there's your purlin, it's a simply supported purlin, and then the total area that is contributing to the load on it is 10 square meters. I would use this area here to design it if it's category H1 or H2, and I'd get to some sort of load somewhere between 0.25 and 0.75. Sorry, I mean, yeah, 10 square meters, I would get to a load there. And oh, just to note there, this, I'll be perfectly honest, coming back, in terms of that A, I find this a little bit ambiguous. This clause to me is not clear. A is the loaded floor area exceeding 20 square meters. So is that when the area exceeds 20 square meters, do you put the total in, or do you take the total minus 20? Up until now, I've just said this to me is not very well worded, so I've taken it as the total area. A is the full area being designed, but I'm not pretending that's the sovereign call on this, so just be careful of that. It's not brilliantly worded. I mean, the straight wording is actually the floor loading exceeding, so I'd take something like A minus 20 and then design for that, but it appears that it's the total area, so that's a little bit ambiguous. Okay, and then here you go. So this is then the imposed load. So this is reduction factor for floor loads. So you'll see there was up to 80, there was up to 20, and then the load starts dropping. Roof area, different areas. So there was your 3 square meters, and then the roof kPa load starts dropping as the area you are designing gets bigger. The building may be 1,000 square meters, but if you are designing a piece of steel that carries 10 square meters, you use a 10 square meter value here. So, all along I've been talking a lot about reference loads, and what I find students often make mistakes with is that they will get to an answer and they don't really have a feeling of, is that a big load or a small load, or does it make sense? What is useful is to have some reference loads in the back of your mind, and when you calculate a load of 1,000 kilonewtons, what is that? Well, firstly, what is 1 kilonewton? I mean, that is one big rugby player per square meter. So 1 kPa is 1 beast per square meter. What is 10 kilonewtons? It's a car. It's about a 1,000 kilograms is about a VW Polo, and so 1 MPa is 100 VW Polos per square meter. So to get to 1 MPa, you have to stack 100 VW Polos on top of each other, and all of that load rests on a 1 by 1 meter square area. Or it's 1 apple per millimeter squared. And now you'll see the visualization of that is very different. This seems like a massive load, whereas this doesn't seem that impressive at all, but both of those are 1 MPa. So just be careful because it's to how big is your area, because this is 1,000,000 times more than that. So when you get results, convert them in your head into something visual to get a feeling of whether results make sense. Because when you're talking floor loads, it should be a couple of kPa, whereas you're talking column loads or beam loads, then you might have 10, 30, 50, 100 kilonewtons that you are dealing with. So now we're going to finish off with the last thing, just to pose some questions that you can start thinking about, and this will lead into the next lectures. For instance, considering a 10-story building, what factors would influence the wind loads on the building? You've got your wind speeds, higher forces, slowed down or speeded up by terrain and other buildings, influenced by geographical locations. The longer the life of the building, the greater the chance of strong winds, altitude, affecting density, direction of wind, shape of building. And then also, now go have a look through the following sections, because this is going to lead directly into the next videos. These are the sections of the wind loading code you are expected to know. And the wind loading code is quite extensive. There's a lot of good guidance in there. We are not covering most of it. We are only covering very specific portions of it. So make sure you know those portions and you can work with them. So as listed here, and we will be leaving out entire sections on canopy roofs and chimneys and all sorts of other stuff. So just be careful of that. And then, yeah, that's just a reminder of the load, the design life of structures which you will need. Okay, so this takes us to the end of the section, which now will be followed on with wind loading as we start applying these these loads to buildings and, well, learning how to determine wind loads, etc. Thank you.